Hello friends, welcome to our YouTube channel RF Design Basics. In this video I will be taking example of root locus plotting having 3 poles. So in this case we can see there is no zeros and there are 3 poles. So as we have studied as a step 1, we are going to find out those 3 poles. So the first pole is s equal to 0, second one is s plus 1 equal to 0 means s equal to minus 1, and third pole will be at s equal to minus 3. So the total number of poles are 3. And since there is no s in the numerator, there is no zeros. So number of zeros equal to 0 and number of poles equal to 3. So the total number is 3 and also the maximum number of pole is 3. The total number of root locus branch will be 3. That is total number of branches equal to 3. Now we are going to see these poles on the real axis. So let us assume this is 0, this is minus 1 and this is minus 3. As we have seen the condition, the root locus will exist only if there are only 1 or 3 or 5, that means odd number of poles plus zeros available. So there are total number of poles and 0 equal to 3. So if we see this portion, then there are only 1 poles in the right side. That means the root locus exists in this region. In this region, do not exist. Here also it will not exist. And then when we see any point this side, then we have 1, 2, 3. From that point, if I go to the right hand side, we count 3 number of poles. 3 is odd number, so due to that there are root locus in this region, so exist. So we are going to have existence of root locus branches on real axis less than minus 3 and between 0 to 1. All other portion on the real axis there is no roots. So that is our step 1 to find out. Next we will see the step 2. Since the roots on the real axis we can see is starting from 0 and minus 1, because all the branches must start from these points. So one will be starting from here, another will be starting from here, and then here. So when it is starting from minus 1, it will go towards right only because there is only existence. Left side it cannot move because it does not exist. So from minus 1 it will start moving right side. From 0 it will start moving left side, this way and this way. And finally it will meet somewhere and it will break away from there. So to find out that breakaway point, we are going to write the characteristic equation. Since this is a unity feedback control system, so the characteristic equation given by Gs Hs plus 1 equal to 0. H of s is 1, so we can just write 1 plus G of s equal to 0. And now we will do the calculation. Here it is 1 plus k by s into s plus 1, s plus 3 equal to 0. So you can write k as minus s into s square plus 4s plus 3, that is minus s cube plus 4s square plus 3s. And this k is given by this. We are going to take dk by ds. For any type of root locus breakaway point finding formula is dk by ds equal to 0. Means we are going to differentiate this by s and then equating with 0. So it will be, since this is to be equated with 0, minus can be removed and we have 3s square plus this is 4s square. So the differentiation is 8s plus 3 equal to 0, which is a quadratic equation, and we need to solve the quadratic equation. Remember, the value must be between 0 to 1 because breakaway point will lie only between 0 to minus 1. If any values beyond that is coming, that will not be valid value. So here we are going to equate this, and from the quadratic equation we are going to solve it. It is minus 8 plus minus root over 8 square minus 4 into 3 into 3 divided by 2. Divided by 6. So here we have to take 6 because 2a, a is equal to 3. So the value is minus 0.45. When I am taking this plus, then it is minus 0.45. If I take minus, we will get a different value. Let us see what is that value. This value is minus 2.21. So another value is minus 2.21. So as we know that the value must lie between 0 to minus 1. So this is only the valid value. This value will not be valid. So our breakaway point will be minus 0.45. Let us keep this. Then we move to step 3. In step 3, we are going to find out the asymptote. So for asymptote calculation, we have a formula 2k plus 1 into 180 degree divided by number of poles minus number of zeros, where k is equal to, how many roots are there? 3. So it will be 0, 1 and 2. So each value for one root. So it will go up to less than 1 than the total number of poles or roots. Here 2k plus 1 into 180 degree. So we'll take k equal to 0. When you take k equal to 0, you get 180 divided by this p minus z is 3. We know the number of pole 3, number of 0 0. So it is 60 degree. Then k equal to 1, it will become 180 into 3 divided by 3, which is 180 degree. And k equal to 2, we get 180 into 5 by 3, so it is 300 degree. So there will be 3 asymptote having these angles. Now let us directly move to step 4 to find out the intersection of asymptote. This is angle of asymptote. Now we are going to find out intersection of asymptote. How we do that? We take, let's say that is x, intersection is at point x. It will be equal to summation of all the poles minus summation of all the zeros divided by p minus z. As you know that summation of all the poles means one pole is 0, another one is minus 1, then minus 3. There is no zeros, so minus 0 divided by 3. So this value is minus 4 by 3, or we can say minus 1.33. So we have all these informations ready with us, and we'll be using that to draw the root locus. So we have finished the calculation part. Now start drawing it. So first of all, let us draw the imaginary and real axis. So this is imaginary axis, this is real axis, and we'll be doing the marking. This basically is plus sigma, minus sigma, plus j omega and minus j omega. Overall it is known as S plane. Now the points are -1, this is 0, then this side is +1, 2, 3 and so on. -1, -2, -3, -4 and so on. You can also have -1, -2 and like that. We have the points this way. Now first thing we are going to draw is asymptote. For asymptote we have to see the intersection point of asymptote, which we have calculated, that is -1.33, and angles are 60, 180 and 300 degree. So we'll be putting first -1.33, which is roughly here. This is -1.33. From there we will use the protector to find out the angle 60 degree. So this 60 degree, then 180 degree will be anyway in this here, and when we invert this protector we get 300 degree. This is 300 degree. Now let us draw this using a scale. So this is the asymptote 1, asymptote 2, and third asymptote will be in this direction because in 180 degree. So the asymptote is in this direction. So we have done the asymptote. We have taken this angle as 60 degree, then 180 degree and then 300 degree. So 60 degree, 180 degree and 300 degree. Now we need to draw the root locus branches on real axis. On real axis, as we have already seen the existence on the real axis, it was between 0 to 1 and after -3. So those things we can draw between 0 to 1. So this will be the root, and -3 to infinity, it will go like this. This is the root locus available over here. So basically this one is coinciding with the asymptote. That means asymptote will be just beside that. And once it reaches 0 to 1, then it is going to break away. And as you know that breakaway point is 0.45. We have calculated the breakaway point also over here. This is the breakaway point. So minus 0.45 is exactly near the middle, little bit towards this side. Let us say this is minus 0.45, and from there it is going to break away. So it will be break away like this, and it will follow the asymptote. It is breaking away like this, and it will follow the asymptote. So this is how you can draw the root locus plot. Now suppose I want to know some more information from this root locus plot. For example, if I have been given with the damping factor as 0.5, then how to calculate what will be the corresponding value of k? In this case, you can see this is k equal to infinity, this is k equal to infinity, this is also k equal to infinity. So if damping ratio is given, how to calculate where will be that value? What will be the corresponding value of k? Question number 1. 2. If I ask what will be these intersection point, because I have just randomly shown -1, -2. We don't know exactly what is the value of this intersection point. It may be intersecting here or here, so we need to know that point. How to do that? For that purpose, we are going to write the Routh-Harvey's criteria. First, we'll find the value of k for which it is crossing the imaginary line, which is called marginally stable. Marginally stable. So we are going to write the expression of characteristic equation, which is s cube plus 4s square plus 3s plus k equal to 0. This is our characteristic equation. We can use the Routh-Harvey's criteria, which I have already discussed earlier, to find out the stability conditions. So it will be like this. Here I can put s cube coefficient, then 3s coefficient, this coefficient, so that is 3, then 4, this coefficient, and then k. So after multiplying 4 into 3, 12, minus 1 into k divided by 4, we get. And this side is 0, and here when we multiply with this, minus 0 divided by this is k. As we know that k must be greater than 0, this to have marginal stability, one of the component in the first column must be equal to 0. So here we can see 12 minus k divided by 4 may be equal to 0 for having marginal stability. One of the term will be 0. So k is equal to 12. So when k is 12, at this point k is 12. Also at this point k is 12. K started from 0 over here. K is 0 over here. K equal to 0. And here also k equal to 0. Then it has become 12 here and then infinity here. So after k equal to 12 means this side, these are unstable region. So we can't take k value more than 12. And 12 is also marginal stable. So the corresponding value of s will give you the imaginary axis intersection point. And to find that, what we do is we just take this as auxiliary equation. So it is 4s square plus k equal to 0. So s square equal to minus 12 divided by 4. So s is equal to plus minus j root 3. So you can see at k equal to 12, what will be the corresponding value of s? S will be plus j root 3. And here it will be minus j root 3. So these are the value for the marginal stability. The roots are s equal to plus j root 3 and s equal to minus j. We know that for marginal stability, our roots will be complex and they are conjugate of each other, and it will be purely imaginary. There is no real part, because if there is real part, root will be lying in the left hand side of this vertical line. So left hand side is fully stable, right hand side is unstable, and the on the line will be marginally stable. For this purpose, when you have been given with damping ratio, how to calculate that? Here you can find out theta. Theta is given as cos inverse of this zeta. So you will get 60 degree. So you need to draw this 60 degree line by taking the protector at the center. And the 60 degree will be from the left. So from left, if you count 10, 20, 30, 40, 50, 60. So this will be 60. Now we can draw this line like this. And the intersection point, if I am using a proper graph, I can read the value of this intersection point. And that intersection point is basically minus 0.35 plus j 0.6. This is the intersection point over here at this point. So this is root locus. We have drawn this angle and we got the intersection point as minus 0.35 plus j 0.6. So if we take this value as the root, and we can find out the corresponding value of k. Let's see how. We have root is s equal to minus 0.35 plus j 0.6. Magnitude of, for this condition, magnitude of g of s and h of s should be equal to 1. So magnitude of h of s is already 1. So magnitude of g of s also should be 1. So k by s into s plus 1 into s plus 3 magnitude must be equal to 1. So we can find out what is the value of k. K divided by what is s? Minus 0.35 plus j 0.6. Then we have s plus 1. So 1 will be adjusted over here. So it will become 0.65 plus imaginary part is still j 0.6. Then 3 minus 0.35 becomes 2.65 plus j 0.6. And then magnitude. It must be equal to 1. So let us take the magnitude of this below thing using the calculator. We have 0.35 square plus 0.6 square, that will be the magnitude, and the value is 0.69. So the magnitude of the first one is 0.69 multiplied by the magnitude of second one. Second one, there is only one change. This value is becoming 65. So it is 0.8846. Then value is 2.65. So you can take 2 here, then do the multiplication. It is 2.71 equal to 1. So we can calculate what is the value of k. K is, we are going to multiply 0.69 into 0.8846 into 2.71. So the value is 1.65. So the value of 1.65 will give you a damping ratio equal to 0.5. So similar way we can find out other damping ratio and corresponding value of k also for a stable system. As we know that if there is damping, it is a stable system. And let us look back into this and find out the reason of unstable. So this portion is unstable. This portion and this portion is unstable. And these portions are stable, and this is obviously stable in the left hand side. So I hope you have got a detailed idea of drawing a root locus having total 3 poles. In next video I will be also taking another example where there will be 4 number of poles. Thank you.